Okay, the second part of the motion unit relates to what causes motion. So the first part, we quantified motion by talking about where something was, how fast it was going, excuse me, its acceleration, and acceleration when in free fall. Now we're looking at, what causes motion. What causes motion is unbalanced forces. If some forces are unbalanced, then something will move, and that's understanding forces is really where we're going. So, just a simple little example here on an airplane. You think everything should be balanced, and if things are balanced, then you have then you don't have an acceleration. This saying thrust is a forward force, drag would be wind resistance, and whatever's causing lift, which we'll talk about much later in the course, and weight is like the force of gravity pulling down on something. So quickly, force is a push or pull. You should know that. I know that you probably learned that in elementary school. Force is similar to acceleration, velocity, in that it has a direction. So it's a vector. Of course, you can measure it, and we have a great, easy little lab you can do after this lesson using little spring scales to measure forces and just get an idea for measuring forces and how you do it. The unit for force is an odd one. It's called the Newton. N for Newton, and it's all based on Sir Isaac Newton, who we'll talk about a bit more later on. An example of using the term force, I can say the force I apply to my coffee cup is 2 newtons west. So I'm pushing on my coffee cup towards the west, applying a force of 2 newtons to the west. And we're going to be calculating lots of forces later on. Why do we care? Well, there's 2 reasons we care. Because unbalanced forces cause motion, or acceleration more specifically, and balanced forces prevent acceleration. So, for example, you've got a bridge and you don't want it to move, then you need to be able to balance your forces. And if you're thinking about a field such as civil engineering, which is architecture, highways, things like that, there you care about balanced forces. If you're looking at a mechanical engineering field or biomechanical engineering, which of course is the body, and that'd be nursing or doctor, then you care about a lot unbalanced forces, right, in the body, or balanced in the body. Deep down, there's 4 what we call fundamental forces, and this is really beyond the scope of a first physics course. But just to give you an idea that, we're going to tell you about all different types of forces, but really they all fall into these categories, and I just wanted to tell you what they were. The first type of force is gravity, and we do talk quite a bit about gravity in the next unit. The second type of force that we work with is electromagnetic, and we will do a whole unit on electromagnetism, but even more than that, and the reality is that every force that we work with and deal with is actually an electromagnetic force. The 2 other forces, the biggest force that exists is called the strong force, and if you remember from chemistry at some point, grade 9 chemistry, you would have learned this, that inside the nucleus of every atom, so think really small, think of atoms, you've got the nucleus with all these little protons, these positively charged particles. Well, they should want to repel each other because they're both positively charged, but something called the strong force holds the protons together, holds the nucleus together. So we're very lucky for that, otherwise we wouldn't exist. And then there's this weak force, and it's what causes like decay of atoms. So if you ever hear of atoms decaying over time, it's caused by the weak force. And again, the strong force and the weak force are really beyond the scope of this course, besides just knowing what they are. So what we'll study, just quickly, we'll study gravity. And it is, of course, it's not only it's the force that causes us to stay on the ground, but it also causes any 2 objects to be attracted to each other. We usually only deal with it between us and the ground, because the Earth is so huge. But gravity is also the reason the Earth orbits the Sun and the Moon orbits the Earth. And our Sun orbits the center of our galaxy, and there actually is no center of the universe that we're sure of. Besides you, someday I'll tell you why you're the center of the universe. But of course, we know it's gravity that caused by the Moon that causes the tides. So a couple of things, details about gravity. We give it the symbol Fg. Every force, we give it a symbol F with some little letter to represent the type of force it is. So F for force and G for gravity. Every force is measured in newtons. There's 2 formulas. We're only talking about one right now, and that's this one, where Fg equals mass times 9.8. Notice this is just like our acceleration due to gravity. So this G is only valid on the surface of the Earth. If you're anywhere else in the universe, 9.8 is just not the number. We talk about something called the normal force. We'll spend a whole day on this, but it's kind of a neat thing. It's the idea that there's a reason we don't fall into the center of the earth. And this is crazy to talk about, and I think I'll talk about it more in class than I will right now. But there's this idea that we, if you remember studying the atom, and you might remember Bill Nye saying that atoms are mostly empty mass or empty space. If you think about an atom, you got your. If I drew a little dot of chalk on the blackboard, a tiny little dot of chalk, and pretended that was the nucleus, the nearest electron would be by the water tower. And all the rest is empty space, not air, nothing. And the question is, why is it we don't fall through the center of the earth? And it's an electromagnetic repulsion is what it is. It's the fact that our electrons in our body repel the electrons in the atoms on the floor. It's a bit deep, but the main thing that we care about is we make an easy calculation to understand that, and that's this normal force. And again, we'll spend a whole day on it, so we don't need to worry about it too much. Oh yeah, I have a little, I think this will come up, a little animation of the normal force on a roller coaster, just to show you. Normal force is always perpendicular to the surface, and so this, I like this little GIF because if it comes up, yeah, here it is. So it just shows you that on a roller coaster, say you're going through, depending on where direction the surface is, the normal force is always perpendicular to the surface. So it's at the bottom of the hill, it's straight up, but at the top, it's down because it's away from the surface. And that's really what normal force on a normal force is. I'm going to shut that down so it doesn't slow down my computer. And come back to our video here. Okay, we'll get more into normal force another day. Spring force, we'll study that a little bit in the next unit, and it just is the force that makes a spring want to be its natural length. You can picture a straight spring, it's comfortable, you stretch it or you squish it, then you have to apply a force, and that's the spring force. Static friction is the force that prevents an object from starting to slide on a surface. So if something's, in this case, you got a vault or a safe, and you want to start it moving, it takes a lot of force to get going. You're overcoming the static friction. And again, here's its symbol. We'll talk a lot about these calculations later, so don't worry too much about it. Kinetic friction is the force of friction acting on an object that is already sliding. So often we call kinetic friction sliding friction. So it's the force you're pulling on. You're pulling on something, you want to get it going at a constant speed. It's what you're overcoming to keep it going. And it's usually less than the force you need to start it. And again, we'll talk more about that another time. There is another type of friction that we don't really deal with called rolling friction. And you can imagine that's, if you had something sliding versus something rolling, the amount of friction is a lot less on rolling. But we don't calculate rolling friction in high school. So we do talk very briefly. Tension is another force, air resistance. We don't do much with these. We'll do a lot more with the other types of forces. Then there's this thing we call the applied force. And it's just if you push on something, you pull on something, you sort of manually do work. That's what we call applied force, okay? And it's F and A for applied. Okay, this is important. There's two types of diagrams related to forces. One is called a system diagram, and it's like you draw a picture of whatever it is you're talking about, in this case an airplane, and I just draw little arrows to represent the direction of all the forces acting on it, and that's a system diagram. Then there's what we use more frequently, which is called a free body diagram. And a free body diagram just means that instead of being an artist, which I certainly am not, and drawing an airplane, I draw a circle, and that circle represents my airplane. And then I draw arrows that represent the forces. And sometimes you're often specific on how big the forces are with numbers. And the only other little thing is something personally, I never use a ruler and draw them to scale. However, if you're going to be absolutely perfect and more perfect than I, you would. So what I mean by that is if the force is balanced up and down on an airplane, like it's not dropping or lifting or anything like that, you could say that the lift and the gravity are the same. Then my arrows that should be exactly the same size, but opposite direction. And see how my thrust, whatever's pushing it forward, is 20,000 newtons, and the drag, the air resistance, is 5,000 newtons. If I was going to draw it perfectly, this one should be 4 times bigger than this one. But the most important thing that I care about as your teacher is that it's clear to me this one is bigger, so you can see it's going to be accelerating in the forward direction, in the direction of the thrust, because it's clearly bigger than this one. That's the most important thing. Then there's something called net force, and we call net force the sum of the forces acting on an object. And to be more specific, especially in this course, we only deal with a certain direction, so the net force up and down or the net force left and right. In this case, for this picture I have here, we've got the net force up and down. And so we give it a symbol F net, like NET is my little lowercase. It has a formula, which we'll talk more about another day. And you can calculate the net force just by looking at this and saying, I always say net force equals up minus down, or forward minus backward. So this thing, it's got to be up. In this case, it's up minus down because it's clearly moving upward or accelerating upward. So that would be 200 minus 50 or 150 newtons up, right? Because it's the bigger minus the smaller. Okay. And notice it has a direction. Okay. So that's it for the introductory note on forces. We're going to do more with free body diagrams and net force in the upcoming lesson.